Hey guys, Miss Peterson here, and welcome to AP Chemistry Lecture 5-1, where we're going to be talking about collision theory and how these chemical reactions actually happen, with talking about the rates of these reactions and how fast they happen. We'll be talking about reaction energy profiles and what a catalyst does to that reaction energy profile. This lecture covers topics 5.1, 5.5, and 5.6 of the AP Chemistry course and exam description, as College Board says. So let's get into it. Now, how do molecules actually react? Well, they have to run into each other, okay? That's the basics of all chemical reactions, okay? They must collide. But it's not just enough for them to collide and hit each other. They have to collide in a specific orientation, okay? And with enough energy to cause those bonds to break and those new bonds to form. If we look at this example over here, okay, where we have, this looks like an NO3, probably one of those nitrate ions, reacting with carbon monoxide to create NO2 gas and carbon dioxide, as we see in the actual chemical reaction. Now, in order for that to happen, one of the oxygens from that nitrate has to collide with the carbon atom because that's who it bonds with. So if you look at this one, okay, and they're moving too slowly, they'll just bounce off of each other. If they're not facing the right way, if we have oxygen running into that nitrate rather than the carbon atom, they're not going to react because there won't be the electrons needed to form that bond and form that interaction. So you need to have enough energy and the proper orientation. Now, sometimes we'll talk about homogeneous versus heterogeneous reactions. And in a homogeneous reaction, that just means that they're all in the same phase. For example, they're all gases, okay? Where if you have something like a liquid interacting with a gas or a solid interacting with a liquid, those are heterogeneous reactions. They have different phases. Okay? So let's get into this energy and how that all works. This is what we call a reaction energy profile. On it, you can see the potential energy, normally in joules or kilojoules, which is the energy stored in the chemical bonds of the reactants versus products. Okay, so in this one, this delta H, that's a little large, is negative, okay? And that is called your reaction energy. Or sometimes you'll see it called reaction enthalpy, which is just the chemistry word for heat energy, okay? Now, in this one, the reactants have more energy, and that makes it an exothermic reaction. So reactants lose energy, okay? The energy of the reactants is higher than the energy of the products. Okay, we have that negative delta H. Now, if it was the opposite way around on this chart and the products were like up there, okay, then it would be an endothermic reaction. And in an endothermic reaction, the reactants gain energy. Okay, so the energy of the products is greater than the energy of the reactants, and it has a positive reaction energy. Now, there's one other thing that we talk about in terms of these, which is the activation energy, EA. Okay, and that is defined as the energy needed to start a chemical reaction. Okay, as you can see here, the reactants don't just fall into products. There's a little activation energy that needs to happen. Classic example of this is, think of wood burning. Okay, when wood burns, you have to light it. But once it's burning, it'll just keep burning because it's generating its own energy. Okay? It has a high activation energy even though it's an exothermic reaction. Okay? And that's the difference between the reactants and the activated complex, which is just the moment of collision. Okay? That moment that those two reactants have collided. Okay? And they will either fall into products or stay as reactants. Now, often when we're looking at this reaction energy, only some molecules are going to have that much energy. Okay? If you're in your shower isn't boiling, but you still have a lot of liquid water turning into gas. You can see that evidence in the condensation of your mirror. That's because at any given temperature, okay, say cold versus hot in this one, temperature is the average kinetic energy. So kinetic energy, if you remember, is 1/2 mv squared. That one is on your equation sheet, where m is going to be the mass of the particles and v is going to be their speed or velocity. Okay? So if the activation energy is, say, there, then more of the molecules in the hot sample will have enough energy to overcome and start those successful collisions, where less of the cold sample would have enough energy. And temperature is a measure of the average kinetic energy. Okay, cool. So in chemistry, we often want to make things go faster. Okay, we want to produce drugs faster. Sometimes we don't want things to happen. We want to prevent our statues from rusting. Okay, we want to make more energy faster. Okay, anything that we want to do in chemistry, we need to control the rate of that chemical reaction. And there are 4 ways here that I have to help that. Okay, the first way is to get those particles closer together. You can either do this by decreasing the reaction volume, which increases that concentration. Again, concentration, I'm typically talking about molarity, which is the moles per liter, or the number of moles divided by the volume, if you want to think about it that way. So, if you have a bigger volume, you're going to be less concentrated. Okay? If you have a bigger volume, okay, a smaller volume, then you're going to be more concentrated. Keep it how I have the words there. But of course, the reverse is true. If you have a bigger volume, you're going to be less concentrated, and that would make the reaction go slower. Okay? You can also increase the number of moles of a reactant, which is just another way to increase concentration. Okay? Increasing the number of moles to increase that molarity. You increase the temperature. That increases the speed, which you can think of as the energy of the particles. So you're going to have more of those highly energetic collisions. If you break up the large particles, that increases surface area. So now you're going from here where only some of the surface could interact, to a situation where you got the clumps floating around, okay, and all of the sides are available for interaction. Okay? And then there's also these things called catalysts. And catalyst is just something to help the reaction along. And we'll be going deeper into how those work later in this unit. So if we want to increase the rate of the reaction, how do we measure it to know that we increased it? Well, we look at the change in those concentration of one of the reactants or products over time. So you can think of the rate as the change in concentration over time. Okay? Sometimes it's a decrease in reactant concentration, sometimes it's an increase in the product concentration. And there's a couple different rates that we measure. Because if you think about it, this is going to change as the reaction progresses. Okay? So sometimes we'll talk about the average rate, sometimes the instantaneous, and the initial rates will be especially important when we get to our differential rate laws. Okay? Let's start with just looking at an example here. Okay? So we have this reaction of C4H9 chloride, okay, C4, whatever, that molecule reacting with water to form C4H9OH and hydrochloric acid, HCl. And they have a graph to show how the concentration or the molarity of that reactant changes over time. So we can get the initial rate. We can tell that it started at an initial concentration of 1.1. Okay, and then as the reaction progressed, okay, the rate slowed down. Now, why is that the case? Well, if you're reacting some of it, you're gonna have less there. So as it reacts, the concentration decreases, which slows the reaction. Okay? That makes sense. If you have less molecules there, you're going to have less of those effective collisions. Okay? If you have more particles, you have more effective collisions. Less particles, less. So we can see that change in it and how we would measure the instantaneous rate from the line tangent to that circle, or the derivative of it if you are a calculus person. Okay. Now, how we actually do this is really specific to the chemical reaction that we're investigating. Okay, so we'll learn to use a spectrometer or a colorimeter, and that's if one of the products or concentration is colored. Think about that blue copper chloride that we've seen before. Okay, if a gas is produced, we could measure the amount of gas produced, okay, through either the change in pressure or collecting that volume of the gas over water. If it's a precipitate, we could measure the mass of that precipitate after letting it react for certain amounts of time. Okay, we can also use pH meters, conductivity probes, and things like that. Okay, and I want us to be able to read these in a couple different representations. So here we have a particle diagram showing a reaction happening where we have purple, which is our A, turning into green, which is our B. So that is the basics of this reaction. And then we can tell we started with 50A, we ended with 50B. So it's a 1-to-1 ratio, okay? Not ration, ratio. For every 1A that goes away, we can see here about half of them have gone away in 10 seconds. So we have that much of B being produced. Okay. Now, if we wanted to find the instantaneous slope of this, we would find the slope of the curve at that point. So we're going to go ahead and try to do that, the rate of change in A at 20 seconds. Are we going to be able to be that accurate or precise with trying to find the slope off of a line on a sheet of paper? Probably not, but we'll do our best. Okay. So the main thing when you're drawing the line is you want it to just touch the area that you're finding the tangent at. Okay, so I'm going to put my line there and use a little bit of computer magic to make it so that it's there. And then so that it's just touching our A line. And then you want to rotate it so that it looks about equidistant from the points before and after it. So I'm going to go with about like that. And looks pretty straight. This distance looks pretty similar to that distance. It'll be good enough. Based on how you draw your line, your measurements might be slightly different, and that's okay. So if I'm using that line, I can see here it's at 20 molecules at 10 seconds. Okay, and then the next point that's going to be easiest to get here is probably here where it's at 30 and about 2 seconds, I would say. Okay, so the rate of change or the rate of the reaction is the change in the concentration of A over the change in time. Okay, basically rise over run. Okay, so that A, again, that's our number of molecules. So that's our rise, and the delta T is the time. That's our run. So we have, it goes from 20 to about 2 in 30 to 10 seconds. So about 18 molecules in 20 seconds. So I'm going to estimate, need a calculator for that. About 0.9 molecules per second are reacting. Okay, cool. Okay, cool. Now, if we know one of the rates of reaction, we can use that to predict the other rates of reaction for the other species. It's not like we need to measure them all independently because they're all interchangeable. Okay? So let's look at this example. Okay? The decomposition of hydrogen peroxide. So for every 2 H2Os that go away, we get 1 O2 and 2 molecules of water. We're going to go ahead and plot those changes on this graph. Okay, so we have the blue already, that is the H2O2. I'm going to go ahead and use red for my oxygen gas and green for my water. So let's actually start with the water because that is a 2-to-2 or 1-to-1 ratio. Might make things a little bit easier for us. So if we look, for example, at this point on the graph, okay, where 2 molecules of H2O have reacted. How much water have we formed then? Again, we're going to assume we started with no water in our system, just pure hydrogen peroxide. And if 2 molecules of H2O have gone, we've formed 2 molecules of H2O. So that would be at that same time in the diagram. Okay. Now, if we look at the next data point that we have, where 6 molecules of H2O have reacted, well, 6 molecules of H2O would produce 6 molecules or moles of water. So we would have 6 moles of water at that point. Okay. We can start sketching this. Over here, we're down to 3. Okay, so we started with 12, so now we're down to 3. So that means 9 moles have reacted, which means that 9 moles of H2O have formed. So we'd be up here at 9 at this point. Yep. And then keep that going. Okay, this looks like we only have like 1 mole left. So we'll have created almost all of it into, okay, well, let's see. That's about 10.5 moles of H2O. So we'll have about 10.5 waters there. Okay. So there's our production of water. Now, let's go ahead and try it with the oxygen gas, which is going to be a little different. Because again, if we start at this point, we're going to assume we started with none. If 2 H2O have reacted, I've only formed 1 oxygen gas. So that one would be down here. Okay. If 6 H2Os have reacted, well, it's a 2-to-1 ratio. So I've formed 3 oxygen gases. So here, the oxygen line would only be about there. Okay. Keep it going. If I've formed 9 waters, I've formed 4.5 oxygen gases. Okay. And let's see, if I've formed, we can work backwards that way. If I've formed about 10.5 water molecules, I've formed about 5.25 oxygen gases. So about there. So there's our O2 line. Okay. So how are the rates of oxygen gas and water related? For every 1 O2, we get 2 H2O. Okay. We get twice as many waters for every 1 oxygen. Okay. Now, how does the increase in oxygen gas compare to the decrease in the concentration of hydrogen peroxide? Well, for every 2 H2O2s that decompose, we get 1 O2. So the rates are a 2-to-1 ratio, just like that stoichiometry. Okay? You can't have that oxygen gas appearing if we don't have that hydrogen peroxide decomposing. Now, one of the ways that we'll write this relative to each other is use a shortcut, which is just to place 1 over whatever that reaction is. So the reaction of H2O is 1/2 the reaction of the change in the concentration of O2 over time. Okay, oxidation is going to appear at half that rate. So half the rate of the H2O2, which means that's also going to equal, and that one's going to be positive because it is appearing. Okay, it's a product. Negative, it is disappearing or reacting. And that will equal positive 1/2 of the change in H2O over time. Okay. Now, for some reason, that is confusing to my brain. I'm like, okay, wait, the rate of oxygen, I know the rate of oxygen is half the rate of water, but writing it in that form for some reason messes with me. So you could always multiply them all by the same factor and say the rate at which H2O2 goes away over time is going to equal twice the rate of O2 over time. Okay? For every 1 H2O that goes away, we get the rate of H2O2 is double the rate of oxygen disappearing. Okay? And that's equal to the rate of water appearing over time. Okay? Those two rates are twice as fast as the oxygen will appear, which we can see on the graph as well. Okay? So whichever way you like it is totally fine. Go ahead and try the practice on your own. Write the relative rates of the reaction. So remember, for the product, it's going to be negative. So the change in the concentration of the pH 3 over time is going to be 1/4 of the rate of change of the P4 over time, or that rate is going to be 1/4 the rate of the pH 3 over time, and that one's going to be positive because it's appearing, which would be equal to 6 times the rate of the H2 gas appearing. Yep. Okay, cool. Okay, cool. And that's it for our intro to reaction rates. Have a great day.